In this video, we're going to understand the very last thing we need to finalize our simplex method. We're going to discuss how we can find an initial basic feasible solution. Based on what we have seen so far, if we have an initial basic feasible solution, then we are able to run the simplex method until an optimal basic feasible solution is found. And we've also understood how to avoid cycling. So finding an initial basic feasible solution really is the last thing we need to understand. In example 3.5, where we fully run the simplex method to an optimal basic feasible solution, we were able to obtain an initial basic feasible solution very simply. In that specific example, we had a problem with constraints of the form ax less than or equal to b and x greater than or equal to 0, where the vector b was greater than or equal to 0. In order to obtain a basic feasible solution, we then introduced non-negative slack variables s, and so we rewrote the constraints in the form ax plus s equal to b, where x and s are greater than or equal to 0. And for this new problem, it's trivial to obtain a basic feasible solution. In fact, we only need to set x equal to 0 and s equal to b. This is a basic feasible solution, and the corresponding basis matrix is the identity. As you can see here, the assumption that b is greater than or equal to 0 is fundamental, because otherwise this basic solution would be infeasible. Therefore, if in our given problem the constraints are of the form ax less than or equal to b, x greater than or equal to 0, where b is greater than or equal to 0, then we can obtain such a basic feasible solution in a super simple way. However, in general, finding an initial basic feasible solution is not easy. In this video, we will see how we can do that. And essentially, to find it, we need to solve another linear programming problem that is called the auxiliary linear programming problem. So now let's consider the general case. We look at our general linear programming problem in standard form, which, as always, has the form minimize C transpose x subject to ax equal to b and x greater than or equal to 0. Here we can assume without loss of generality that b is greater than or equal to 0. In fact, you only need to look at the equalities where the right-hand side is negative and multiply such an equality by -1. So from now on, we always assume that b is greater than or equal to 0. Now we are ready to introduce our auxiliary problem. And the way we obtain such an auxiliary problem is in a way similar to what we discussed just one slide ago for that linear programming problem with a very special form. In fact, also here we want to add non-negative slack variables, which in this case we're gonna call y. If you think about it, we don't really need here to introduce slack variables. In fact, we already have equality constraints, so it really makes little sense to add a slack variable. However, we will soon see why this is useful to us. Now, what about the objective function of this auxiliary problem? This is simply the sum of all the y variables. At this point, the connection between the original problem and the auxiliary problem is unclear. However, what is clear is that, similarly to the special case that we considered one slide ago, also here, it's very simple to obtain a basic feasible solution for the auxiliary problem. Everything we have to do is set x equal to 0 and y equal to b. Also in this case, the corresponding basis matrix is the identity. In this slide, I have written again my original problem on the left and the auxiliary problem on the right. Remember that our task is to find a basic feasible solution to the original problem, and what I just told you is that we're able to find easily a basic feasible solution to the auxiliary problem. Now let's discuss the connection between these two problems. The key observation here is that if the original problem has a feasible solution, let's call it x, then the same x together with y equal to 0 gives us a vector that not only is feasible to the auxiliary problem, but it also has 0 cost. Now the contrapositive of this statement is that if the auxiliary problem doesn't have a zero-cost solution, then there is no feasible solution to the original problem. If we now look at the auxiliary problem, it is clear that the cost of every feasible solution is greater than or equal to 0. This is because the objective is the sum of the y's and they are all non-negative. Therefore, the auxiliary problem has a zero-cost solution if and only if its optimal cost is zero. So what we have shown is that if the optimal cost in the auxiliary problem is non-zero, then the original problem is infeasible. And this is great because remember, for the auxiliary problem we know a basic feasible solution, therefore we can run the simplex method on the auxiliary problem until we find an optimal solution. This optimal solution then gives us information about the original problem. So we've understood that if the optimal cost of the auxiliary problem is non-zero, we can conclude that the original problem is infeasible. So what if instead the optimal cost in the auxiliary problem is zero? Then the optimal solution is a zero-cost solution to the auxiliary problem. And if we look at the objective function, it means that we must have y equal to 0 in such an optimal solution. And if y is equal to 0, it means that x satisfies ax equal to b and x greater than or equal to 0. Therefore, we have found a feasible solution to the original problem. So all in all, what did we obtain from this auxiliary problem so far? By solving this auxiliary linear programming problem, we either understand that the original problem is infeasible, or we understand that it is feasible and we also obtain a feasible solution. This is close to what we wanted, but it's not exactly what we wanted. In fact, if the original problem is feasible, we don't want to find just a feasible solution, we want to find a basic feasible solution. And on top of that, we also need an associated basis matrix B, so that we can construct the corresponding tableau. It turns out that by solving the auxiliary problem with the simplex method, we can easily obtain such a basic feasible solution, the basis matrix B, and also the corresponding tableau. How can we do that? There are two cases that we need to consider separately. The easy case is when the auxiliary problem terminates with a basis matrix B that consists exclusively of columns of A. Remember that in the auxiliary problem, the constraint matrix is formed by A in the first n columns and then by the identity matrix in the remaining m columns because of the addition of the slack variables. So let's now understand this easy case. If we write down the optimal tableau of the auxiliary problem, it will look like this one. In this tableau, I have added one vertical line here to divide the columns corresponding to the x variables from the columns corresponding to the y variables. The optimal cost is 0. The reduced cost will take this form. To obtain these reduced costs, you just need to recall the definition of the reduced costs and use the special form of the constraint matrix that we just discussed. The remaining rows of the optimal tableau are B inverse B, and then we have B inverse times the constraint matrix. So B inverse A here and B inverse here. Since the basis matrix B only contains columns of A, I can simply drop the columns corresponding to the artificial variables and use B as a starting basis matrix. The only other thing that we need to do is to replace the 0th row, and this is because the objective function changes from the auxiliary problem to the original problem. So we only need to recompute the 0th row using the original cost vector C. In these tables I use the red C to indicate the costs in the auxiliary problem, while I use a black C to indicate the original costs. At this point we're done. We have our basic feasible solution with basic components B inverse B. We have our basis matrix capital B, and we also have our starting tableau over here. We didn't even need to recompute all of it. We only needed to compute explicitly the 0th row. So this concludes the easy case. So now let's consider the harder case, which is when the basis matrix B contains columns corresponding to the artificial variables y. To recap, in this case, the auxiliary problem has an optimal cost that is 0, and it terminates with the feasible solution x star to the original problem, where some of the artificial variables are in the final basis. In particular, this must be a degenerate basic feasible solution to the auxiliary problem. And this is because in the optimal solution, all the y variables are equal to 0, and at least one of them is in the basis. we will see that in this case we will be able to obtain a different basis of the same solution x star that consists only of columns of A. So how can we do that? We first understand this algebraically in this slide, and later on we're gonna see how to do this directly in the tableau. So let K be the number of columns of A that belong to the final basis, and so we're assuming that K is strictly smaller than M. By eventually reordering our constraints, we can assume without loss of generality that these are the first K columns in the basis. So these are AB1 until ABK. These columns are of course linearly independent since they are part of a basis. At this point we need to find M minus K additional columns of A such that, together with this K, we obtain a basis of Rm. Now we need to use our assumption that the matrix A has full rank. This means that there exist m linearly independent columns in A. And it is a basic fact of linear algebra that there exist m minus k additional columns of A that, together with our k, form a basis of our M. Now, if we use these additional columns to obtain a new basis, we indeed obtain a new basis for our solution x star. And this is once again because of our old theorem 2.4. In fact, we just need to observe that all the non-basic components of x star are at zero level. So if we are able to obtain this new basis, then we're done because we reduced ourselves to the easy case where all the columns of the basis belong to the matrix A. And so the artificial columns can be dropped. We recalculate the vector of reduced costs, and we end up with an initial tableau for our simplex method. So in principle, at this point, you know how to do this, as long as you remember from linear algebra how you can complete a basis. If you don't remember that, don't worry, we're never really gonna need that because I'm gonna give you an easier way that allows us to make all the computations inside of the tableau. But in principle, this is the easy way to understand what we're gonna do inside the tableau. The procedure that we just described is called driving the artificial variables out of the basis, for obvious reasons. And in this discussion, we used the assumption that the matrix A has rank M. On the other hand, if A has rank strictly smaller than M, then not only this construction will not work, but no construction can work. In fact, it's clear that there are no m linearly independent columns of A. Therefore, there cannot be any basis at all that uses only columns of A. So it's really important to construct our auxiliary problem only once this assumption holds. If you remember, we can always reduce ourselves to the case where the rank of A is equal to m, and this is done by removing redundant constraints one by one, as we discussed in theorem 2.5. Also here, dropping redundant constraints is a simple exercise of linear algebra, because everything you need to do is check linearly dependency of vectors. However, also in this case, we will never need to do this explicitly, because also in this case, we're gonna carry out these computations directly inside the tableau in a very simple way. Let's see how. Let's say that we have one basic variable, xbl, that is also an artificial variable, which puts us in this hard case. In our tableau, the nth basic variable corresponds to the nth row. So here it is, xbl. In particular, since this is an optimal solution to the auxiliary problem, we have that xbl will be equal to 0. Since xbl is an artificial variable, the corresponding unit vector with 1 in the row L will be a column corresponding to the artificial variables. Therefore here, in this blue zone, which is at the right of my dividing line that divides the original variables from the auxiliary variables. Now we search in the nth row of the tableau and only in the columns corresponding to the original variables for a non-zero entry. There are two cases. Either we find a non-zero here, or they simply are all equal to 0. Let's consider separately these two cases. In the first case, we have found one non-zero entry, which I highlight here in yellow. This will be the column corresponding to variable xj, with j between 1 and n. Now we claim that the corresponding column of the original matrix, which is AJ, is linearly independent from the columns AB1 until ABK. How can we show that? We're going to use once again our standard trick. Namely, we only need to show that B inverse AJ is linearly independent from B inverse AB1 until B inverse ABK. So essentially, we multiply all our vectors by B inverse on the left. The reason we do that is because now checking this linear independency is very simple. In fact, let's look at the nth entry of these vectors. Well, the nth entry of B inverse AJ is exactly our yellow entry, which is non-zero, while on the other hand, B inverse times ABI is equal to EI for every I from 1 to k, and since k is strictly smaller than L, the nth entry of all these vectors is equal to 0. We have thereby shown that Aj is not a linear combination of the vectors AB1, ABK as we wanted. As we've already discussed, what we want to do now is to bring xj into the basis, taking the place of xbl. In other words, we want to bring aj into the basis and have the nth basic variable exit the basis. And we know that this operation can be performed with a pivot. Everything we need to do is to perform those elementary row operations that replace the jth column, which is B inverse AJ, with the nth unit vector. So we need to obtain a 1 in the pivot element and a 0 everywhere else in the column. This is almost exactly equal to a pivot that we've always performed in the simplex method. The only difference is that in our case, the pivot element is simply non-zero, while in all our previous pivot, we always had that the pivot element was strictly positive. So essentially here, it could be also strictly negative. Now, what happens to our current solution when we actually perform the pivot? To understand what happens to the solution, we just need to look at the 0th column of our tableau. In the elementary row operations that we perform, we add a multiple of the pivot row to the other rows. But now, since xbl is equal to 0, the values of the basic variables doesn't change. Therefore, after the change of basis, we are still at the same basic feasible solution to the auxiliary problem. However, we have reduced by 1 the number of basic artificial variables. Now let's see the second case. In the second case, when we look at the nth row of the tableau, then in the columns corresponding to the original variables, we find only zeros. This means that the nth row of the matrix B inverse A is equal to 0. The nth row of B inverse A is the product of the nth row of B inverse with the matrix A. So if we denote by G transpose the nth row of B inverse, we obtain that G transpose A is equal to the 0 vector. In other words, the 0 vector can be obtained with a linear combination of the rows of A. Therefore, A has linearly dependent rows. So this second case can never happen if we assumed in the first place that A has linearly independent rows. However, if we find ourselves in this situation, it means that the matrix A that we started from had linearly independent rows and we didn't realize that until now. In this situation, we immediately obtain that we also have G transpose B equal to 0. This must be the case because we know that our original problem is feasible because the optimal cost of the auxiliary problem is 0. Therefore, the constraint G transpose AX equal to G transpose B is the trivial constraint 0x equal to 0. Therefore, it is redundant and it can be eliminated as we have seen in theorem 2.5. This constraint is exactly the information provided in the nth row of the tableau. So in our tableau, we can simply eliminate that row and continue like if we never had that row. Now let's see an example. In this example, I want to show you how we can obtain an initial basic feasible solution to this linear programming problem using the technique that we just described. We notice that our linear programming problem is already in standard form. Before writing the auxiliary problem, we need to check that the right-hand side vector is greater than or equal to 0. This vector b, in this example, is equal to 3, minus 2, 5, and 1. So we have a negative component that is this minus 2. Therefore, before writing our auxiliary problem, we need to multiply the second equation by minus 1. We will obtain minus x1 plus 2x2 plus 6x3 equal to 2. So now we're ready to write down our auxiliary problem. In the auxiliary problem, we add one slack variable per constraint. So in the first one, we have plus x5, then plus x6, plus x7, and plus x8. And all these slack variables are greater than or equal to 0. We trash our original objective function and instead we minimize the sum of all the slack variables. Also in this example, I always highlight the auxiliary variables in blue so that we don't get confused. So let us now focus on our auxiliary problem. Our auxiliary problem is constructed in such a way that it is now trivial to obtain a basic feasible solution for it. This is the solution obtained by setting all the original variables to 0 and by setting the vector of auxiliary variables to b, which is a vector that is greater than or equal to 0. Since the basic variables correspond to the auxiliary variables, the basis matrix is the identity. We can also calculate immediately the cost of the solution. By just plugging our basic feasible solution in our objective, we obtain that the cost is 3 plus 2 plus 5 plus 1, which is 11. Now our target is to form the initial tableau. So what else do we need? We need the vector of the reduced costs. As always, the formula is C transpose minus CB transpose B inverse times the constraint matrix, which is A and the identity. What is our vector C transpose? This is the cost vector of the auxiliary problem. So it is the vector that has zeros in all the original variables and ones in all the auxiliary variables. Then in our formula for the reduced costs, we have C transpose B. So what is this vector? This is the subvector of the basic components of C, and since the basic variables are exactly the auxiliary variables, we have that CB transpose is equal to 1 transpose, so the vector of all ones. We can now substitute C transpose and CB transpose in our formula for the reduced costs. We obtain that the vector of the reduced costs is 0 transpose 1 transpose minus 1 transpose times the inverse of B. Remember that B is the identity, so the inverse of B is also the identity. And finally, times A and the identity matrix. So in the components corresponding to the original variables, we obtain 0 transpose minus 1 transpose times the identity times A. Therefore, we just obtain minus 1 transposed A. For the auxiliary variables, we obtain 1 transposed minus 1 transpose identity times identity, which is simply 1 transpose. So 1 transposed minus 1 transposed is equal to 0. So our vector of reduced costs takes this simple form. In the auxiliary variables, we simply have zeros, and in the original variables, we need to sum all the rows of A and take the negative of the result. We are now ready to form the initial tableau. Let's deal with the 0th row at the very end. Let's first consider the remaining rows. In the 0th column, we have B inverse B, and again, B inverse is just identity, so this is the original right-hand side vector. In the remaining columns, we have B inverse A in the black part, which again is simply A, our original constraint matrix, and then in the columns corresponding to the auxiliary variables, we simply have B inverse times the identity, which is the identity. Now let's look at the 0th row. In the 0th column, we have the negative of the cost, so minus 11. In the columns corresponding to the auxiliary variables, we have all zeros, as we have just seen. And in the columns corresponding to the original variables, we only need to sum the remaining entries in the column and change sign. In the first columns, we have a 1 minus 1 plus 0 plus 0. So this is a 0, and the negative of 0 is again 0, and we write it here. In the second column, we have 2 plus 2 plus 4 plus 0. This is 8, and so we write minus 8. And so on and so forth with also the third and fourth column. Finally, since my basic variables are x5, x6, x7, and x8, I write the corresponding labels here on the left of the tableau. Now that we have formed the initial tableau for the auxiliary problem, we can start to run the simplex method. Also in this example, I will be the pivoting rule, so I will break ties as I want to. We have 3 negative reduced costs, and I choose x4 to enter the basis. To determine the variable that leaves the basis, I need to look at the positive entries of the corresponding pivot column, and I only have one of them, the one over here, so I will have x8 to leave the basis. We now have to perform the pivot. In the pivot, I need to obtain all zeros in the pivot column except for a 1 in the pivot element. So as you can see, this is a very easy pivot because I only need to modify the 0th row. The 0th row is obtained by summing the 0th row with the pivot row, and if you perform this sum, you obtain this new tableau. In particular, the cost of the solution is now 10. I still have 2 negative reduced costs, and as your pivoting rule, I choose x3 to enter the basis. Now the positive components in the pivot column are all of them, 3, 6, 9, and 3. So I need to compute the ratios and choose the smallest one. For the first basic variables, the ratio is 3 divided by 3, so it's 1. For the second one is 2 divided by 6, which is 1/3. For the third is 5 divided by 9, and then is 1/3. The smallest among these numbers is 1/3, and I have a tie between the variables x6 and x4. As your pivoting rule, I choose x4 to enter the basis. So my pivot element is 3, and now I need to perform all the elementary row operations to transform the 3 into a 1 and everything else on the pivot column to 0. If you perform these elementary row operations, you obtain this next tableau. The cost is now only 4, but I still have one negative reduced cost, which is minus 8. The positive entries in the pivot column are 2, 2, 4, and the corresponding ratios are 1, 0, and 1/2. Therefore, I will have x6 to enter the basis and take the place of x2. Note that theta star was equal to 0, so this will be a degenerate pivot. If you perform the correct elementary row operations, you will end up with this tableau. The pivot was degenerate, and so the cost is again 4. But again, I have 2 negative reduced costs. I have minus 4 and minus 2. I break the tie by having x1 enter the basis. The positive entries in the pivot column are 2 and 2. And the ratios are 1 and 1. Again, I have a tie, and I choose x5 to leave the basis. So my pivot element is this 2 over here. If you now perform the pivot by making the elementary row operations, you will obtain this tableau. As you can see, the cost is now reduced to 0. So we have found a feasible solution to the original problem. However, as you can see, we're unfortunate because x7, which is an auxiliary variable, is still in the basis. So we need to drive x7 out of the basis. What we need to do is to look at the entries of this row corresponding to the original variables and check if they're all 0 or not. In this example, they are all zeros. This means that our original constraint matrix A has linearly dependent rows. As we have discussed, in this case we can just throw away this row. We obtain this new tableau, and note that there are no more artificial variables in the basis. So now we can obtain an initial tableau for the original problem. To obtain this initial tableau, we need to do two things. First, we erase all the columns corresponding to the artificial variables. So all this blue part of the tableau is trashed, and this is the tableau that we obtain. But we're not done yet. In fact, we still need to recompute the 0th row. To compute the reduced costs, we use the formula for the reduced costs. C bar transpose is equal to C transpose minus CB transpose B inverse A. In this formula, C is the original cost vector. If you go back at the beginning of the example, you will see that it was the vector 1, 1, 1, 0. This is because the objective function was x1 plus x2 plus x3. Now from the tableau, we read that the basic variables are x1, x2, and x3. So the vector CB in the formula is obtained by taking the first three components of C. So we have CB is equal to 1, 1, 1. What else do we need to compute? to compute our reduced costs. We need to compute B inverse A. This is easy because we know that the matrix B inverse A is the tableau without the 0th row and without the 0th column. So it is this part of the tableau. Now we have all the elements to compute C bar transpose. If you do the calculations, you will obtain that C bar is 0, 0, 0 minus 1/12. Finally, to fill in the 0th row, you need to compute the cost of the solution. The solution can be read in the 0th column, so you just need to evaluate the objective function on this factor. If you do so, you obtain 11 divided by 6. So in the top left corner, we will write minus 11 divided by 6. So now if we take this tableau and fill in our new 0th row, we obtain this tableau in this new slide. This is an initial tableau for our simplex method, and so we can now start executing the simplex method on the original problem. As an exercise, please finish running the simplex method starting from this tableau. Before moving on, I want to mention one more thing about example 3.8. I want to give you a simple trick that in the future it might be able to speed up your exercises by sparing you a bunch of calculations. The key observation here is that when we created the auxiliary variable, we didn't really need to introduce the variable x8. The idea is that the variable x4 plays a role in the problem that is symmetric to that of x8. What do I mean exactly with this sentence? I mean that x4 appears with a +1 coefficient in the same equality constraint, and x4 also doesn't appear in any other equality constraint. So essentially, in all our discussion, we could have used the x4 instead of x8. So for example, at the beginning, we would have started with x8 equal to 1 instead of x4 equal to 1 to satisfy this equality constraint. In particular, x4 would have been in the initial basis instead of x8. This would have simplified our calculations because we would have had one fewer variable, so one fewer column in our tableau, and we would have also had one fewer pivot. In fact, if you go back to the beginning of our example, in the very first pivot, we had x4 enter the basis and x8 leave the basis. So when exactly can we make this simplification in the creation of the auxiliary problem? It turns out that you can do this anytime there is one variable that appears in a single constraint and with a positive coefficient. So it doesn't even really matter that you have exactly a +1 here for x4. If you had +2 x4, it would have been very similar. Think about what the difference would have been. So if you have a variable that appears in a single constraint and with a positive coefficient, it turns out that you don't need to introduce a slack variable in that equality constraint. I'm not going to give you all the details on how exactly to do that, and I leave this to you as an exercise. At this point, we have fully understood how we can solve a linear programming problem in standard form with the simplex method. The resulting simplex method will be called the two-phase simplex method. Why do I call it two-phase? Well, because the first phase is the one where we need to find an initial basic feasible solution, and then the second phase is when instead we start from such a basic feasible solution and run the simplex, and end with an optimal basic feasible solution. So let's recap our two-phase simplex method. First, we discuss phase 1. We start by multiplying some of the constraints by -1 in order to obtain a right-hand side that is greater than or equal to 0. Next, we introduce artificial variables y1 until ym, and I write here if necessary because we know that in some cases we can avoid introducing some of them. Then we apply the simplex method to the auxiliary problem where the cost is the sum of all the artificial variables. Now there are two possible outcomes. If the optimal cost in the auxiliary problem is positive, then the original problem is infeasible and the algorithm terminates. So let's consider now the remaining case, which is the more interesting one. This is the case when the optimal cost in the auxiliary problem is 0. In this case, we have found a feasible solution to the original problem. Again, there are two cases. If no artificial variable is in the final basis, then the artificial variables and the corresponding columns are eliminated, and we have a feasible basis for the original problem. On the other hand, if the health basic variable is an artificial variable, we examine the health entry of the columns B inverse AJ, for j that ranges from 1 to n. If all these entries are 0, the health row is a redundant constraint and is eliminated. Otherwise, we find at least one non-zero. Let's say this is in the jth column. Then we apply a change of basis to have the health basic variable leave the basis and xj enter the basis. We need to repeat this operation until all artificial variables are driven out of the basis. Once this is done, we can finally go to phase 2. The final basis obtained from phase 1 is our initial basis for phase 2, and we need to form the initial tableau for phase 2. This is obtained from the final tableau in phase 1 by discarding the columns corresponding to the artificial variables and the zeroth row. We compute the new zeroth row by computing the cost of the feasible solution and the reduced costs of all the variables for this initial basis. Of course, we have to be careful to use the cost coefficients of the original objective function. Finally, we apply the simplex method to the original problem. Now, the two-phase simplex method is a complete method, meaning that it can take as input any linear programming problem in standard form, and it will fully solve the linear programming problem. If we avoid cycling, and we know how to do it in a couple of different ways, then the two-phase simplex method will end in one of these four ways. A. If the problem is infeasible, this is detected at the end of phase 1. B. If the problem is feasible, but the rows of A are linearly dependent, then this is detected and corrected at the end of phase 1 by eliminating redundant equality constraints. In particular, note that if you run the two-phase simplex method, in input you need just any linear programming problem in standard form. So you don't need to check yourself that the rows of A are linearly independent, because this is done automatically in phase 1. Then in possibility C, we have that if the optimal cost is equal to minus infinity, this is detected in phase 2. Finally, D, we have that phase 2 terminates with an optimal solution. So now we have a complete method to solve linear programming problem in standard form. And this concludes our video about section 3.5.